Yeah. All right, welcome, folks. This is the kickoff for the 9th Community College Quadcopter Challenge, sponsored by NASA Connecticut Space Grant Consortium. And we're going to just see who we have from different campuses here. So we have people from Asnuntuck. There we go. Welcome, Asnuntuck. Do we have, let's see if I remember all the people. We go Quinnipiac Valley. Yes, that's 2. Do we have Northwestern? Do we have Middlesex? Excellent. We have Manchester, Naugatuck Valley, and Tonkass. Yeah, so we have people from each of 7 teams. Welcome. What we're going to do today is we're going to talk a little bit about the challenge, look at some information about flight on extraterrestrial areas, and go over rubrics, and then I'll cover a few things about basically how quadcopters work, batteries and power, and some additional stuff about motors and things. But this is not going to be like super deep on that, just to try and give you some stuff. And then, yeah, that's the plan for today. So first, who here knew that NASA had put a helicopter on Mars? A number of people, yep. So it's called Ingenuity or Ingenuity, depending on your accent. It is sent up with it's computer-generated video. Take pictures, and as you see, be able to combine those. And it sends the information back to the rover. And the rover send that back. You want to make that it's really slow. It exists, so you can use but it's not a lot of gas. So it's been in vacuum chambers, pulled down to around Mars atmosphere, so they can make it that's fly in the very light Mars atmosphere. Now Mars, thankfully, doesn't have Earth's gravity because gravity somewhere around there. So it's easier to fly. Here is an actual flight. So this was flight 54. You can go online and find lots of play. Maybe it is playing. There it is. Yep. So it's kind of low frame rate. You can see maybe the rotor spinning, and will it take off? There you go. Amazing. So I have some stats on the next thing, so we'll do that. So it started off with a pre-flight wiggle check, so that's why I spent some time doing the rotors there. And then it got up to about 5 meters before now it's gone back down. So this was just, a public flight check, but they did some more interesting flights with it as well. It flew a lot, and it's been decommissioned. No longer fly. But it made a total of 72 flights, over 2 hours total of flight. This was spread out. It didn't have individually very long flights because right, and you're trying to power with solar panels and recharge, whatever. But it ended up flying a total of 11 miles worth of distance and made it up to 24 meters. It's around 80 feet off the surface. So we've demonstrated an ability to fly on Mars. We asked about the RPM. It's around up to 2,800. So that's the revolution from the rotors. You can see it actually had a couple of rotors. So they were on the same axis, but they were spinning opposite directions to try and counterbalance the torque, right? The conservation of angular momentum stuff. But yeah, it would do over a month. It would be able to fly about 5 times with the time to recharge in between. And This I thought was a fun thing from somebody from JPL there. You know, on Earth, the highest altitude for helicopters is 40,000 feet. On Mars, because of the altitude, because of the low atmosphere, it's as if you were up to 100,000 feet up on Earth, just at the surface of Mars. So as you get farther from the surface of the Earth, our atmosphere gets thinner. Mars is as thin as it would be at 100,000 feet. It was a design challenge to do it. And they couldn't directly remote control it. Why? Why do you think they couldn't remote control it? Yeah. So transmission delay, right? We only know, as far as we can tell, the only way we actually can communicate stuff is at the speed of light. And turns out planets away, that turns out to be minutes. And so from the time you send a signal to Mars, it depends on the time of the year, how long the transmission delay is, the relative position of the planets. But it takes that time for the signal to get over there. And then if you're relying on any feedback, like visual or whatever, it takes the same amount of time for that feedback to get back. So it's just not feasible. So it has to be autonomous. That means that just using its own sensors, gyroscopes, etc., it needs to be able to operate without human intervention there. So yeah, we're not stopping there. There are plans to send not just so that was a helicopter, we're sending a multi-rotor vehicle to Titan. You know what Titan is? Yes. It is one of the moons of Saturn, Jupiter, Neptune. Do we have? Let's vote. Saturn. All right. Saturn. We got it. All right, we figured it out.
Sorry.
No, you're good. And the idea is it's going to bring a mass spectrometer to identify components and measure surface composition and other stuff with meteorological sensors. So, and obviously take pictures and images. That's a plan. It's not going to be for a little while, so it's planning right now to launch in July 2028. I'll reserve my editorializing on current NASA mission priorities and stuff, but I really hope this stays towards the top of the list. I think this would be really valuable. Anyway, so what we're going to do is sort of inspired by that. We're going to be, there are specific design things, quadcopters, or drones, or whatever, autonomous aerial vehicles, that are different than they would be on Earth. Now, we're just going to fly ours on Earth, but we're going to have some things sort of inspired by this, and not rely on some things that you could rely on that aren't those other things. For example, most drones reasonably and rightfully use global positioning stuff, right? GPS. And that's great. And you can have your drone use GPS, but for the actual challenge, we're not going to be using it for that challenge. So if you want to have GPS and use it as you fly around and whatever, that's fine. But why would that be? Why don't we have GPS on Mars?
We just have satellites.
Yeah, you need satellites to do that. We haven't put enough satellites around Mars. We could, though. It's a thing that people could do if they wanted to. Anyway. All right. So, I'm going to go over the quadcopter business. Any questions? So, yes.
The whole concept is quadcopter, but I feel it's limited. Is there a way that we could?
Yes, it does have to be quadcopter. I debated. I wanted to change the name, and then we ended up not, just for simplicity. Maybe you folks can all agree on what the name for it should be next year, but just for continuity of the past, we kept it. But yeah, it's one option for the new name would be unmanned aerial vehicle. Right, UAV channel. Right? Anyway, so yes, you don't have to have only 4. All right, quadcopter business. How they work and this extends to other flying vehicles as well. I'll talk about this. You have rotors. You spin the rotors, and they move gas, air, and then you shove it down, and that gives you thrust down, a conservation of momentum that pushes you up. That's how you get your lift, you're directly shoving the air down and pushing yourself up. And as far as controlling how you move, what you do is you adjust the amount of throttle or the amount of power you're getting from each motor so that as you spin them in different proportions, you can make it left, right, forward, back, turn in place, turns for these, yaw, etc. But that's the basics, right? And one thing that's important to note is that to avoid having our things spin in uncontrollable ways, you need to have sort of roughly equally amounts of clockwise and counterclockwise. This isn't the only possible configuration shown here on the right, but this is showing clockwise on the top, or, front left, counterclockwise on the front right, and then reverse for the yeah.
With the newbie into this, are you going to get notes?
Yes, so this, I will provide this whole PowerPoint, and I'm recording it, and we have another recording, so hopefully we'll have this, and we'll be able to put it on YouTube and send that around. And there'll be a Discord, and we'll post stuff. Yeah, that's how it works. So how do you send those signals to the motors? Here's a block diagram. Don't panic, I know there's lots of lines. We're just going to walk through. We start off with, I want to tell it to do something. So I have my transmitter that I move knobs on this. It sends signals to a receiver. So that receiver is plugged into a flight controller. That's the brain of your quadcopter. The flight controller takes in a lot of input and gets a lot of output. So right now, we're going to focus on it takes in the input from the receiver, and then it has to figure out how am I going to spin these motors. And so it sends out this PWM, this pulse, or well, it sends this pulse rate modulated signal stuff out. But anyway, it sends out control signals here to an ESC, which is an electronic speed control. So that tells it, the ESC, how fast to spin the motor. Now the brain doesn't need a ton of power to run. In fact, if you give it too much power, you can fry it. So what you actually do is you power this whole thing with a battery that has a power module that splits off a small amount of power to go and power the flight control. And then the larger amount of power goes to a power distribution module or base plate in the default kit that we have. It just got onto a base plate. What that does is it gives you a place for the high power, more dangerous power to not have to go through the brain directly. Now this can go separately straight to the motor. So the base plate distributes the high power electricity through the electronic seat controllers, and the electronic seat controller takes in that power and the signal about how fast the motor, and then it actually sends out the motor the voltage it needs to spin. So that's the basics of operating. Questions? All right. There are a couple other things shown on here. You can add on more yourself. Here I'm showing a telemetry unit. If you want to get information from your drone back to a base station, just like we saw with Ingenuity, it was sending information back to the rover. You can do that. So you need some way of communicating back to, for example, a computer with a paired telemetry unit, and then you can get flight information back there. You can also, it's very common to just use GPS to help control where you're going, so you get GPS. There's a lot of other stuff you can put on. People have wired in other like servos to this to be able to try and control the position of like the camera or things like that. So you can add on things through your flight controller. You can also add on things other than a flight controller to try and do stuff, either Arduino or Raspberry Pi. There's lots of things you can do here. But that's the basics of how the drone works. So you're going to make a drone. We have either kits or, we'll talk about that. You're going to make it, you're going to design modifications to it to try and accomplish certain tasks. And then we're going to meet back together in April at Central Connecticut State University. This is a picture from last year's challenge. This is a 20 foot by 20 foot by 10 foot tall enclosed cage, so try and keep everybody safe in there. And then you're going to fly around trying to come up. So at the challenge, you'll have 10 minutes to do a presentation. I'll talk about it in a minute. And then 12 minutes to fly around and try and get points from doing different tasks, demonstrating different capabilities. Here's the rubric. It's tiny. Don't bother trying to read it there. But there are lots of different areas. We're going to go through some of this stuff as far as what you're trying to accomplish. So first, the presentation. You're going to present about making this drone. You have 10 minutes. It will consist of a video. So this is a pre-recorded video. That will be 2 to 3 minutes, no more than 3 minutes. You'll have a poster you'll prepare, and you'll be able to have places there to, show a poster. You can also use PowerPoint stuff if you want. Basically, what you're trying to do is you're making your case about some of the tasks. So, a couple of the tasks here, Bladen, just go back just real quick. A couple of the tasks are weight reduction, rotor protection, and camera. So weight reduction is when you're doing your quadcopter or your drone. For flight, weight is really important. Mainly, we generally want to keep it down as much as possible. But you need to have stuff on it to do this, right? So you get points for having a lighter quadcopter. And then if there's innovative stuff you do to try and get the weight down or do that, you get points for that. So the only way the judges know about the weight is you tell them about it during, we can have a weigh-in as well. Like, to know what you did to try and account for that is during the presentation. You don't have a ton of time, but you want to mention that. There's rotor protection. For a lot of things, like if you're flying away from people, a lot of times you don't need rotor protection. But for if you're flying inside and you want to mark up the walls and you bump into stuff, or we have had somebody who cut the arm from having quadcopter. So you can have some rotor protection that makes it so that rather than the rotor hitting something directly, it gives a little bit of protection. We have some like rotor protection we're sending you with, but then we want you as part of the design part of this to design your own rotor protection.
Yeah, weight reduction, because we've done this for a few years, and how should we compare? Is it basically what we were going to use and how we thought of reducing that weight? Is that's what we would say to the judges and demonstrate?
Yeah, so we will measure the weights of the quad.
Individually?
Yeah.
Okay.
Yeah. So we can compare it as well. But then, talking about like why is like, yeah. A camera. So as part of this, some of the tasks involve taking pictures, mapping stuff, designing a camera mount so that you can mount a camera on there, and it says like CAD drawing, same thing with rotor protection. You want people to, even if you're not 3D printing or whatever, like people use a computer-aided design to make up your drawings and you make some transform and that. So this is stuff you can put on your poster and demonstrate during the presentation. And then you can switch between out and down view, so that's looking forward and looking down. It says within 60 seconds, but if it's faster than that, that's good. People try to do that right. So look at the full rubric for the full details on it. But those things right there are all things that you're presenting on in the presentation. So make your case about weight. Same thing, I'll talk about mapping in a minute, but whatever capabilities you've given to your quadcopter, we'll talk about sample collection in a minute, like whatever capabilities it has, make the case for those capabilities, and then you'll also have a chance to demonstrate some of those in action. Yeah, so make it easy for the judges to judge. We'll have the same rubric you have. So, as part of that presentation, there's that video. This should have a flight demonstration. All that means is I've had people do videos in the past where they never included a video of the quadcopter actually flying, and that's like the exciting thing. Like, oh, I want to see your quadcopter video. And it can be a video from outside of the quadcopter flying, or it could be an onboard video from the perspective of the quadcopter, or whatever. You need something like that in there. But then you were describing your quadcopter. You can describe the build process, the capabilities, whatever you think is an interesting and engaging video that helps make your case about why your quadcopter is good. Here's an example video. This is not like do a video like this. This is just showing you an example of a video that's happened in the past. But not at the bottom though. Few words. I think they do talking. They're really close.
It's really weird. It must be going through one set of speakers.
Right. Yeah.
Yeah. I guess probably my phone was perfect. Yeah, because I have
Yeah. Well, all right. You get the idea. They're showing videos of things. They're talking about stuff. You can't tell what they're saying. And the whatever. All right. We'll skip that. This link will be. This has not every single video. This has a bunch of videos including 3 from last year. So go ahead and take a look at previous videos if you want an idea of some sort of things to consider. So that's the video. With the video, one thing I'll add is that you might have people on campus who like to produce videos. You're not restricted to only the people in the team who can participate in this. You can work with other people. So feel free to loop in other people to help with this. We do want it to be like students, not like the fact that advisors are here to advise and give you resources and training and that sort of stuff, but we want students producing all of it. But yeah, also on the videos, I think it was on a slide, but whatever. It can help to have music. Don't use copyright to music that you don't have the rights to use. There's copyright-free or royalty-free music available in lots of places, so look for that and use that. Yes. Yeah, if you own the copyright and you give yourself permission to use it, that's fine. But if you know DMX, you can ask him if you could use it. But you could if you were to, whatever it's fine. So yeah, take a look at them. All right. And last thing, make sure, I think I say it on here, but make sure on the video, credit the speaker. Right? Like you can throw a logo in there. You can just it is what it is. All right. Posters. For making a good poster, you want to answer the question, what's the most important thing about this? How can I get this point across visually? And what can I say about my project on my poster? And this also goes for if you're making any sort of PowerPoint slide for a long presentation, right? You don't want to have tons of words that people have to read. You can have enough words to explain things, but you want to focus on the visual stuff. And I just want to compare these. Here, this is much more visually engaging with large images and enough text to convey what you need to. This is this where it's like the one on the right is mostly text with some images, some of them too small. And, not great. So, yeah. Important information should be readable, legible from 10 feet away. Make sure that you have an interesting title. Word count, this is a ballpark, but if you find that you have like 1,500 words on your poster, that's almost certainly too many. Text is clear and to the point. Formatting to help it so that stuff doesn't just seem like all over the place, and trying to keep consistent fonts. So generally on a poster, you don't need more than maybe one type or two types of fonts. Like maybe you could have like, you don't need tons of font families. You have and serif, and it's like all you might need. Consistent, clean layout, and then importantly, make sure there are appropriate acknowledgements. What that means is all the team members' names should be on the poster. The faculty advisor should be on the poster. The Connecticut Space Grant Consortium should be on the poster. Your campus, CP State with the logo, CP State that's at your campus thing below it, like CP State Quinnipiac Valley. These are available on the CP State website. The Space Grant Consortium logo is available on the Space Grant Consortium's website. So make sure those are on the poster. Important. This is the sort of thing that if you're doing research, you'll see some of them today if you stick around for the expo. There are posters out there that people were funded research. You need to have who was funding that research on your posters. So yeah. All right. So that's like the presentation. Good to go on to some of the actual tasks you're trying to accomplish. All right. So one of them, a basic one is just basic flight capability. That multiple people can take off your quadcopter, clear an obstacle, and land in a location. So you get points for doing that. You get points for up to, you want to have 3 members of a team be able to do that. That's encouraged. So it's not just like, oh, somebody's a good pilot, and then they're the only person who ever gets to fly the quadcopter, right? So that everybody can have a chance, and then you can get points for up to 3 separate people doing that basic takeoff. And then there are the more interesting things like sample return. So designing some way of collecting samples of water, sand, and gravity. You can see sort of how that'll be roughly laid out. And the dishes might be slightly different, but they'll be something like this with water and sand, sand and gravel. And then the water will either be in a 5-gallon bucket, or I'm actually looking at a little bit broader, like tiny kiddie pool type thing. Yeah, so I didn't take a picture to put on here. I do have a tiny button. I'm going to try and do that instead, so that it's not having to hover over this whole bucket. Yeah.
There's still going to be points for autonomous things to get between people.
Yeah, I'll talk about the autonomous software. So we're running it very similarly to last year. I did some feedback form stuff to try and get feedback on things to change, whatever. I didn't get a lot of feedback. So we're doing things in a lot of ways similar that we're trying to improve. Like, we'll talk about some of the improvements, but yeah. So, good question about autonomous flight. So, autonomous flight, that means that you're not directly controlling where it's going. You're having to execute a set routine. So, for example, there are points for being able to, just like we saw in that Ingenuity video, take off, hover, and then land. But that's without you on the throttle. You press one button or whatever to engage it, and then it takes off, hovers, and then land. So you get points for that. You also get points for accomplishing any of these other tasks, like sample collection. If you can do that autonomously, it'd be very impressive. You get additional points for doing that. And to be clear, you don't have to do, like, if you can do it autonomously, you can just do it autonomously, and you get the points for sample collection and the points for the autonomous work. You don't have to, okay, I did it by hand, and now I did it autonomously. You could just go for the autonomous stuff. Autonomous flight.
Space needs to be distances.
So it depends on how you're doing the autonomous stuff. You will, on the day of the schedule, have things laid out and available. I think we said if you need to ride by so that you're all checked in by 12, and then have lunch, and then I think we're starting to get on this plan. The exact time might change, but it'll be something like that. So there's an arrival time, and lunch. You will have time to observe and see the arena at that time. You won't know beforehand. On that day, you'll be able to observe in person and see that. Then you can change your routines of the program, go with what you observe on the day. Yeah, so that's the plan. So there are ways of doing this where you can write stuff to try and autonomously like identify by site and things like that, but things get tricky.
In the history of this program, has anyone done autonomous in these schools?
I think nobody's accomplished some of the more impressive autonomous stuff, but I think one team did do an autonomous takeoff plan. So there have been some points for autonomous flight, but not many. So I'm leaving it on there for now, see if we can get there. One thing to be clear, if you're trying to autonomous flight, either fly it fully enclosed or be tethered by cable to a weight, because when you're doing sort of feedback controller type stuff, depending on your control parameters, things can go out of control. So make sure you build the kill switch first, so that if it goes out of control, you can shut it off, like exit it, like make sure that you can kill the motor, right? But then be safe about it. On the day, you'll have a fully enclosed thing, so you don't have to have it tethered on the day, right? Since we'll have the full ending all the way around. Ways of doing autonomous stuff is dead reckoning. This is using flight control sensors, but no feedback aside from that from the area. So like you use the accelerometers and gyroscopes and whatever to maintain level flight, just like your flight controller is doing that normally anyway. But that would be like making a program that's like, okay, I know I'm starting from here, so I'm going to say, like, try and give it the inputs to make it go forward like 3 meters, and then like rise to 2 meters, go forward 3 meters, drop down. That's dead reckoning, right? Just trying to give it that. You can also have some sort of feedback. So you try and give it that, but then you also give it some visual way or other way of trying to look at how far it's actually gone on that. One thing that I've recommended in the past, but there are other options out there, but there's a thing, Clover, that's based on robot operating system, ROS, that you can have it connected to a flight controller, so it's running, it's a Linux-based thing, so you can run it on your Raspberry Pi type thing, and then have it connect with that, and then sending, so basically instead of the transmitter sending the information over, it would be via a wire from the Raspberry Pi sending the stuff over to the flight controller. The flight controller is still just kind of doing its thing based on the inputs it's getting, and then sending back information from since you're asking for to the separate, a separate thing mounted with it. So that's autonomous flight. It's hard, but mapping. So you can, a lot of people have gotten a number of points in various places of mapping. There are points for making 2D maps. And this is, as you're flying, you can point your camera down and take pictures. And you can try and map. You can also, from a video try and reconstruct a 2D map, or set pictures, try and meld them into a single 2D map. There are various software tools you can try and either write yourself, implement via various open source software stuff that's out there, or use like manual stuff. So you can either have a script you're running or a manual process where it's, you get the pictures back and then I manually kind of rearrange them in scale and try and do that. And yeah, there are various photogrammetry, that's for the 3D, but various ways of merging those together. And you get some extra points for determining the actual scale of the map. One thing that I can tell you, just based on this, we will have, to protect the floor, we'll have some foam tapping. It will be 2 thick squares. And then they're not like super firm edges on it because it's like a little piece, they just lock together. But they are 2 foot squares. So if you want to have something that kind of scales off those, that is a way of trying to get real lengths there are other ways of giving real lengths based on the camera and the distance. And there's also 3D mapping. We've had some people do this in pretty impressive ways using things like LiDAR sensors and stuff like that. So if you get 2D pictures, especially if you have information about the location you were at and took those pictures, it makes it even easier. There are algorithms you can run to stitch those together into 3D surface type stuff from that. So that's the process called photogrammetry. There's also ways of, I mentioned the LiDAR, like, so you can shine out a laser and have it bounce back and then measure the time and figure out how far away the thing is as that happens. There are other ways of doing that. But yeah, so 3D mapping is pretty cool. You can get extra points for 3D mapping. Yes?
During the day of the event, there are times this composite can be challenge, or is it done at the beginning of the day?
Yeah, so it has, right now, the plan is it has to be done by the end of the day. We can look into that for the future. We could possibly implement it. So one thing that you can do is you can, if you have this capability, you can demonstrate it to the judges in your presentation that, hey, look, we have taken this stuff and then here's the map we're able to generate. We're going to take that same information today, but then the process, maybe it's a manual process. But there are some processes that you can get set up that you could actually run it at the same sort of time, right? Complete in a minute or so. All right. Yeah. All right. So that's, I think, most of the stuff that you get points for. This here is the rubric on Google Sheets. I have this. Yeah, I'll share this as well. But yeah, this, I think I've covered everything. Yep. Oh, last thing, photography. There will be some specific targets. If I don't know, I think we'll probably just stick with this. So this is a horizontal target. That will be a target that probably have a QR code on it. Just some level of, you've taken a good enough picture that it can resolve this, right? And like, get information from it. So that's a target that you have to take a picture of straightforward. There's a vertical target. That's a picture that you have to take of looking down at it. And then there'll be points for having pictures or adequately documented all the landscape features. So there'll be various tables or other things inside the arena. So being able to get pictures of everything will give you get points for that. All right. And now those are all the things you get points for. The rest of this is, I'm going to spend a little bit of time here telling you about the basics of factories and motors and things work. As you get into doing the work, you'll discover things that you need to know and you need to figure those out. So your advisors or resources will have a Discord that you can ask other teams. We'll have a mentor that you can ask as well. Will be on the Discord. But this is also about you. Like, this is one of the great things about project-based things is that there's a thing you're trying to do, and then you learn the stuff you need to do to accomplish that. And the stuff you learn while doing that tends to stick with you because you're doing it for like an authentic reason, not because somebody said, "Oh, here's a puzzle you need to solve because I tell you so." Right? Trying to accomplish a thing. So I learned stuff. All right. Basics about like, who here feels like they have a okay grasp on the basics of like electricity? A few people, not many. That's why we're going. So, voltage is a thing you probably heard of. Voltage you can think of as analogous to pressure, or like a pressure drop. So, if you have high pressure water, it's going to come out, right? If you have low pressure water, it's going to drop. Same thing with voltage. If you have high voltage, that gives you the potential to transmit electricity. And then when you're transmitting it, you're transmitting it through like wires and things like that, and those have electrical resistance. So that's resistance to the flow. You think about that like pipes. So if you have a very skinny pipe, it's going to have more resistance to the flow than if you have a big wide pipe. It's going to have less resistance. So it's going to be easier to flow water through a bigger pipe than a smaller pipe. Electrical resistance is called that in an analogous way, and it's measured in ohms, or this Greek letter omega. You can see as a symbol for it. And the higher the resistance, the harder it is to flow electricity through that. In general, just like with pipes, tinier wires will have higher resistance for the same length than larger wires. So you'll see on these, we'll have tiny wires for some of the electronics, and then have thicker wires for the power that's going to our motors that need the high power, need a lot of electricity going. And current is how much water is coming out of the pipe. Similarly, in circuits, current is the amount of, I'm being a little imprecise in how I'm saying this. I don't want to get too like nitty-gritty and stuff, but the amount of charge you're shoving through. And so the combination of your voltage and your current gives you the total amount of electrical power. All right. So power is how hard the water is coming out of the pipe. And you can imagine if I get a higher voltage and a higher current, you'll get more power. Right? So batteries, we're going to be powering these with batteries. There are lots of symbols on batteries. Here we see something that says 3S 11.1P 2200 mAh, in parentheses 24.4 WH, 30C, 66 amp, maximum continuous discharge. So lots of info here. We're going to just try and understand what this means. So first, batteries are electrochemical, or combinations of electrochemical cells. So the electrochemistry inside is what determines how much voltage you get out of a certain cell. And then you combine those cells to get higher voltage. So for our LiPo, that's lithium polymer battery, you have a nominal voltage of 3.7. So it has a certain, like that's the nominal voltage. You design stuff at 3.7. When you actually fully charge it, its actual voltage is going to be higher. It's not like linearly related to the amount of energy stored, but it is related. So you charge it up. If you have a single cell, it can charge up to 4.2. You can try charging it higher, but you shouldn't because that's dangerous. So you charge it up to 4.2 at the max for each cell, and then I should have had discharge on this, but the minimum healthy discharge for this is 3.5 volts. So when you're discharging this, if you go below 3.5 volts, it will negatively impact the life of your battery. And then the minimum safe discharge is 3.0 volts. So you really don't want to go below 3 volts per cell. So this right here has 3S at the beginning. That means 3 cells in series. That's where the S comes from. So if you take a 3.7 volts and put it with another 3.7 volt in series, they just add. So here this has 3 of them. So if I have 3 of 3.7 series, how much total voltage do I get? So 3.7 times 3.
Oh,
11.1. So you get 9 plus 2.1. Anyway, you get 11.1. And that's what this is. 3S, 11.1 volts. So that's saying you have 3 cells in series that gives 11.1 volts. You can get these that are 3S. I think the ones that we by default are 3S. You can get them that are 4S. You can get them that are 6S. That'll change the voltage, and you want to make sure that whatever electronics you're running with works fine with whatever voltage you're going. Anyway. So that's the voltage. Then there's capacity. So the next thing is 2200 milliamp hours. It's not my favorite way of displaying capacity. I would prefer just an energy, but this is how they're displayed. And it's how much energy you can store. So a higher milliamp hour number will give you longer performance. Lower milliamp hour will last for less time. That's the amount of energy it can store. And you can estimate the flight time by looking at the capacity and the average amperage draw. And so dividing those, that'll give you the flight time. And that's why it does the milliamp hours, because it can be like, well, if I measure my current draw in milliamps, I can just do the simple division, it'll tell me my flight time. You will not get hours flight time out of any quadcopter unless you specifically design it to be super long range, right? But you're looking more, depending on the battery, anywhere from like 5 to 15 or 20 at the top. Probably what you'd be looking at. I'll mention that most racing batteries, for like the smaller but faster, more nimble, agile ones, are going to be either 4S or 6S. That's what they tend to use. They tend to, I'll talk about some of that. All right, and then you have, so made it through the top part. Now we have this 30C. So this 30C is the discharge rating, and it's how fast you can safely discharge the battery. And it's a little bit weird because it interplays with the capacity. 30C, that means you take 30 times the capacity. 30 times the capacity gives you the maximum safe discharge in amps. This tells you if I have a 2200 milliamp hour battery, so 2200 milliamps, that's 2.2 amps. Do people know milli prefixes? So 1,000 millimeters is a meter. Same thing here, 1,000 milliamps. So we have 2.2 amps times 30 gives you 66 total amps that you can discharge. So when you're looking at batteries, if you're looking to buy some spare batteries, whatever, that's the thing to keep in mind. You might be like, oh, this is fine, but wait, my C value is less. Like I bought a higher capacity battery, but now it's a lower C value. Is that enough? We can just do this multiplication. See, will it be able to give me, will I be able to draw enough amperage or enough current to do that? And you want to make sure the electronic speed controllers aren't the bottleneck on this. Well, yeah. So yeah, if you want to be able to draw more amps, you might need a speed controller that's bigger or small. Generally, the battery won't. So there's the battery, the speed controller, and then the motor. You just want to make sure that you're getting enough power to the motors, so the motors aren't struggling.
Just by size.
Yeah.
With more milliamp speed, heavier battery.
That's correct in general. Yes, more milliamps means heavier battery. Also, higher S, so like 3S to 4S, that's going to be heavier battery as well. Now you do get, with higher capacity, you do get longer flight time, but it's not always as obviously a win as you would think, because kind of like with flying planes, they try and fuel them just enough to make the trip, because the more fuel you take, the more weight you have, the more fuel you have to use as you're flying. Same thing with this. The higher capacity battery is, the heavier it is, the faster it's going to drain. So the higher capacity should more than compensate for that, but it's not like, oh, I want it to fly twice as long, so I use twice the capacity. It won't fly twice as long. It will fly longer, but not twice as long. Then you'll have more mass, so controlling your quadcopter with more mass can sometimes affect how easy it is to control. Safety on these things. Pick it up by the body, not the leads. So like the wires coming out, don't pick it up. The body. Charge it in a fire-safe bag, and preferably attended. I know nobody does this, people just leave them unattended, but I'm telling you to, so don't get mad at me. These things can catch on fire. If they're hot, don't charge it. I know this can be tempting, but like if you're pulling it off the thing and you're like, I need to charge to get going, but it's hot coming off the quadcopter, don't charge. Maybe you were flying out in the sun and it got let it cool down to room temperature. If it's swollen, just decommission it. Yeah, put it in a freezer or something. Maybe, I don't know, I haven't played. You definitely can. I just don't know what level. Like you don't want moisture and ingress stuff. But like you can definitely, it's definitely safe to like run a fan. Yeah. So that's the thing. Like you don't want it to get to thermal extremes on either end. It's definitely safe with room temperature air to blow fans a little bit to help cool it down. And that's actually how in electric cars, for example, they're all, well, I think some of the early ones might not have been actively cooled, but they're all the modern ones are all actively cooled. Where yeah, yeah, yeah. And then set your balance charger correctly. So what I mean by that, yeah. Yes, and in fact, I recommend, I think we, do batteries. I recommend you have more than two. Because two gives you enough where you fly it and then you can switch it out to another orange battery. But what if you need to switch it again? Right, so like, four, I think good balance on what to do. I debated just buying extra batteries, but I decided I'll let you decide what batteries you want. So you can decide if you want to try higher capacity or lower capacity or higher S, maybe you trying to, go with higher, like different motors or things. So anyway, yeah. There was something else I was going to mention about, whatever, we'll keep going. The safest charge rate for most batteries is 1C. That means it's 1 time the capacity of the battery in amps. So for 2200 milliamp hours, what's the safe charge rate for that? 2.2 amps, right? Whatever this is in amps, the 2200 milliamp hours, the 2.2 amp hours, that means that the fastest you can charge that safely is 2.2 amps. Now, if you want to give your batteries longer life, charging them a little bit slower will help them have longer life. This is another reason why it's kind of nice to have more batteries so that when you're going and flying and doing stuff, you can keep swapping out, maybe start one charging, not like. And yeah, I explicitly mentioned you can buy other batteries. All right, questions on batteries? Now, there's like a lot of information. I've been talking for a while. We're getting close to the end, I swear. Well, the end of this part, we'll have some stuff after as well. I'm going to talk about motors. The types of motors we tend to use on quadcopters are brushless DC motors. DC is direct current. It's just a type of motor. Take a physics course if you want to understand how electric motors work, or like electronics course. So all I'm going to, they work via electromagnetic induction. So the brushless part is that you have, I said I'm not going to talk. It's cool though. So instead of brushes switching around things, you have solid state electronics switching how hard it's plugged to keep it spinning out. And you're using permanent magnets along with electromagnets, with coiled up electromagnets to have those interact to make your thing spin. All right, that's the brief description. The power you get comes from the battery. So I alluded to this before. The power the battery provides is the current you're drawing times the voltage. That power goes to spin the motor and provide torque. And the power of the motor is going to be the torque that it can provide, or that it's using times the speed that it's spinning at. What that means is based on the balance of how you do this, you can have higher torque, lower speed motors, or higher speed, lower torque motors. But based on the power source, like you can't get power from nowhere. Right? Whatever power you're trying from the battery, that's what you can get into your motors. Okay? It's going to be drawn from the battery and split between however many motors you have. If you have a quadcopter, that's 4 motors. If you have a hexacopter, like you get 6 motors, right? And you have to be able to split it up and have enough power for each of those motors to spin at the speed they need to spin. There's a thing that you'll see on motors when you're trying to, well, there are a couple of things to see. This one right here is a little small, but it says RS2212 920 kV. So this kV thing is the velocity constant, or the speed constant, it's sometimes called, but velocity makes more sense to it. And it has units of RPM, that's revolutions per minute, per volt. So if you want to know how fast this thing will spin, you can take that kV, multiply it by the voltage, you should remember if you have a battery. So you multiply by the voltage, and then that's how fast it can spin with no load. It's in practice going to spin slower than that because you're going to have a load on it. You're going to have a rotor, and that rotor is going to be moving air, and so it's not going to spin as fast as no load. But this is just basically, the higher that you get here, the higher the maximum speed that you get. And the higher you spin your rotor, everything else being equal, the more air you displace, so the more thrust. Yeah. Yeah, so in practice, actually, what you do is there are design equations for this. I've included some links to them, and then you can also look them up on your own. That's really if you're designing motors yourself. We're not going to design motors, probably. It would be cool if you did, take your own line. But you can look up either if you find motors that have tables where somebody's done this, or you can do this yourself. You get like a strain gauge or some sort of force sensor, and you attach. You've probably seen this with like rockets, where they have a rocket engine and attached to a fixture, and then they're just blasting the rocket engine, and they're measuring the force to see how much thrust it can get. You can do the same thing with rotors, where you have to set it up so that it has enough clearance so that the rotor can be attached. But yeah, you just attach that to a stationary thing, and you can measure the thrust. And so you can actually, if you want to do this, you would need one of those. I looked at some. I found something for like $1,000 for like a nice thing. You can probably design one on your own for less. But anyway, a lot of people, depending on what you're looking at, somebody might have done a bunch of those tests with various different propellers and various different power sources, like 3S versus 4S, like powering different things. So you can look up in thrust tables what that is and just try and find, okay, so this motor, if I power it this way, I can get this much thrust. If you have higher battery voltage, that'll also give you higher speed and more thrust. You need to make sure that your motor and your electronic speed controller can handle it. But yeah, that can be a thing. And then if you have, all things being equal, bigger propellers, that displaces more air, so you get more thrust in them. These are ways to get more thrust. For stable flight, you want to have at least 2 times the thrust of your quadcopter. For acrobatic flight, you want more than that. We're not really, in general, doing acrobatic. There's no like going through hoops, like this is not a race. So you don't necessarily need to target that sort of behavior, but you want to have enough thrust. We have had, this is why I added this in, because this has been a thing that's happened a number of times. So not like this is, you're all novices, we're all learning, and we're, but try and head some of that off. One of the things that happens is you're designing your stuff, you're adding on things, you add on weight to do your things, and now your quadcopter is really heavy and it's just barely making it around. And that means that it's really hard to maintain stable flight, because you can tune your control parameters all you like, but if it needs to make this rotor start spinning fast enough to stabilize stuff, and you're already almost at the limit, it just bumps up like, I can't spin any faster, now it's not controlled. So you need to have enough headroom over standard operation to be able to correct and keep stuff in control. And then what does the 2212 mean? That means the stator is 22 meters in diameter and 12 millimeters in height. You can find like 2206s, you can find like all sorts of things. The larger your stator volume, the higher the torque. You don't always want high torque power, like that's what that is. And you can always look at actual thrust tables where it has a motor with an actual propeller on it to see what thrust you get from that. And I say you always can, you can't always. If it exists, you can. Not all motors have thrust tables.
You calculated the volume by.
Yep. And this is more ballpark than some of this other stuff, because this would be like if it's like for like. So if you're doing the exact same materials and lines and that, but it turns out using different material, like different motors have a lot of things that are varying on them other than just. But yeah, if everything is exactly the same, then that's that. Here are some links to that, so take a look at that. Last bit on, last bit on this sort of thing, propellers. So here are some propellers. These are labeled as 1045 CW, CCW. These are self-locking, they don't have nothing to stop. The 1045, that means 10-inch diameter, which is like the length here. If you look at this, it's the length of the rotor. And then 4.5-inch pitch. This is a little bit more complicated, but it's how, based on the geometry here, it can scoop in different ways to try and shove air at different rates behind it as it does a complete spin. So this is saying it's one complete spin, it's trying to shove the air 4.5 inches as it goes. So yeah, that's big. And the larger diameter produces more thrust and is generally capable of lifting heavier loads, but it needs more motor torque to run it. So if you have a motor that doesn't have enough torque to run it with the larger stuff, moving to a smaller propeller can sometimes help fix that, or you need a bigger motor. Smaller diameters are more efficient for higher RPMs. So if you see the like really acrobatic tiny quadcopters, they tend to run at very high RPM with small. Yeah.
The 4.5 inches, is that physical, or is it physical care?
It's the air displacement. Yeah, so the depth of this is 100 inch, right? Like the actual like physical dimensions here. So this is the actual physical dimension, but this is the air. So kind of like a screw sort of pitch, that idea that as you turn it, how much does it advance? And in practice, it doesn't add anything. That's design. And so for the higher pick that you have, the more bite of the air you get with each turn, right? So lower pitch, you're shoving less air behind you as that goes. So anyway, higher pitch gives you higher speeds for everything else being equal. But as with the length, you need more power. Okay. And then the CW means clock. Can you tell me what CCW means? Brilliant. So, yes, importantly, if you have a rotor that's supposed to be turning clockwise, it needs to have a clockwise rotor. Like, if there's a motor that's supposed to be turning clockwise, it needs to have a clockwise rotor. If you mismatch those, then what will actually end up happening is that you're turning it one way and it's shoving air the other way. So instead of shoving air down, it shoves air up. And that's good. Or maybe you put the rotors in the right spots, but maybe you didn't label your motors in your software correctly. So you're spinning your motor in the opposite direction. And make sure your motors and rotors are matched in the spin and how you think. Yes.
Some has to be counterclockwise and some has to be clockwise. How about the third? You have like another third. Where would you?
So with quadcopters, you have four.
We have maybe 6 rotor.
Yeah. So with I gave one possible configuration for a quadcopter. That's not actually the only way that you can have those rotors. You are going to have 2 that are clockwise and 2 that are counterclockwise, so that it's balanced. But it doesn't have to be in the configuration I did. It's just depending on what it is, how you control that. The flight controller needs to know the orientation so that it tries to spin them the right way to move. So if you're doing a 6-rotor design, then you're going to want equal amounts, clockwise and counterclockwise, 3 of each. But then as far as how they're laid out, there are multiple different ways of doing that, and your flight controller just needs to know which way you're doing. There are positives and negatives to different ways of setting those up, so you can look online, try to decide, try stuff out. Configuration, just make sure that it is like, because the motors will have clockwise threads and counterclockwise threads, so that you can imagine if it was all the same thread and you're spinning, it could be working the rotor free as you go. And so the motor itself, if you change to a different configuration of which things are spinning which way, you need to physically move the motors, because the motors internally are pretty much the same, so that's why they can spin the other way. But the threads on the top are not the same; they're opposite threads. So you need to physically unmount the motor, mount it in the new position, and make sure that's the same with the software.
To confirm, You have to use 4 propellers.
No, no. So it's called Quadcopter Challenge. It's, but you're welcome to do whatever unmanned aerial vehicle you think can accomplish. I would advise against fixed wing airplane type stuff just because we don't have enough space in the 20 by 20 foot to do that easily. So some sort of helicopter-ish thing you want, but it could be a hexacopter, it could be, you know, there's lots of options.
Even singular.
Singular, yeah. Yeah. All right, I've got some safety stuff. Wear safety glasses. You might not want to. You might be like, oh, I'll be fine. You probably will be fine. But you only have 2 lives. And we're not good at replacing. Yeah. You might be like, but I'm so far away. Yeah. Right. What happens is you have things spinning. There's a lot of kinetic energy in the rotational motion of the rotors. If they crash into something and break off, that can come flying at high speeds. Even if they don't, sometimes just as you're landing and there's more dust than you thought, and it kicks up the dust, like you just, that can be going fast. So, you know, safety glasses, rotor guards. If you're flying outside away from things, sometimes you can get away from that, but especially if you're trying things or you don't know that it has stable flight yet, make sure you have that. Stay a safe distance, don't fly over people. And for autonomous attempts, just emphasizing either be fully enclosed or have a cord tag and be ready to pull. So that's the safety stuff. Here's the legal stuff. If you fly inside, it's fine. So if you get permission from whatever campus you're on to fly inside a gym or whatever, I would recommend if you have mats or something to help protect the floor in case you have crash landing, like that's a good idea. But, you know, if they let you fly inside, hey, great. And maybe they'll let you fly inside until you mark the walls. If you're flying outside, which is where a lot of people end up flying for a lot of it, to do that, you have to first pass trust that the 3 lines in linked here. Then you have to register your drone, link there. You have to label the drone with, you know, the flight number on it. So this can just be like a piece of paper. And then you have to have a remote identification broadcast. Now, as of right now, we haven't bought any of those, but I have one that we'll just buy and send it out to people. It's like $30. I have the link as well. So if you don't have one of those, the only place you're legally allowed to fly outside these days is in an FAA recognized ID area. I think Peter at Middlesex, yeah, got part of Middlesex as one of these as a free so that you don't have to have that on, or you can just be flying outside in that area. But if you don't have one of those things established, then he can help you. I don't want to promise it, but he figured it out how to get this done. So if you want to do that, so you don't have to worry about that. That's fine. You fly outside, you fly inside or at the actual challenge. And then follow the safety guidelines. We are operating under the recreational flyers exemption for educational use. If you're part of an institution that's approved, which we are because it's an institution of higher education, you can use the recreational flyers exemption. So there are certain rules around that, follow those rules. If you fly, if you don't fall under the recreational flyers exemption and you're under a certain size, which all are really, then you can park on this. That requires other stuff. So for us, we're going to fly at or below 400 feet when in uncontrolled airspace. We're not going to fly in controlled airspace. So if you're near an airport, don't fly there. You're going to keep your drone in your line of sight. Recreational flyer, that's required. Don't fly over groups of people. And here are the full links to educational users that, in case you need to justify to a dean or anybody, this has from the official government.gov sites. Educational use qualifies as recreational flyers here. As far as, let's do this. Before you fly, there are a number of different, so I have the link to the, here you go. So this link is in there. There are a number of different desktop and mobile apps. You can get some of these as apps on your phone as well. But let's just click on Aloft here. Oh, that's right. Because let's just All right. Now? Thank you. All right, so here, we have this is the thing I have a link to. So there are a bunch of things. You can look for the apps if you want the apps. But then Aloft, here I just chose one. I gave it permission to see my location, and then it automatically is like, yeah, you're here. Now, if you notice, if I zoom out, if I tried to fly here, it's like that's controlled airspace. So you can, if you have Part 107 thing, like there are ways of flying there, but we can. We just can't under recreational flyers exemption. Over here, more controlled airspace. So where we currently are is like over here somewhere. If you click notify and fly, you can see like it gives you like don't go over there, right? So if you're too close, it'll still let you, but here we'll cancel. Put us closer. See how it overlaps? You can still take off and land here and whatever, but like we're pretty close. So just be careful about that. Anybody want to give me a place to look at? You want to give me a location? Whatever. You can play around with this on your own. All right. Back to here. And there are a bunch of others. That was just ordering stuff. So how this works, we have some kits for some teams here today, and then we have kits that we're going to order and send to other teams. Apologies, but we'll get them sent to you. Probably ordered on Monday and sent out from there, so it should arrive soon-ish. So some of that we'll be able to do today. For ordering stuff, on top of the kits we provide, there's, like, in none of the kits, we never include a camera. If there's a kit from a previous year that has the cameras and switches, you might have a camera. But that's a common thing that you have to buy is the camera. Lots of different types of cameras. There's FPV cameras, which are first-person view cameras. You can get things that then you can like either wear goggles or see it on a screen from the point of view of the drone live. That's kind of cool. A lot of times the image quality of those is not great because it's trying to emphasize like low latency for live flying rather than image quality. But there are action cams. There are lots of other options for cameras. You might want to buy backup parts. I already mentioned you should probably buy extra batteries. And as far as doing this, there's $1,000 limit. So you have a budget on top of the kit of $1,000 to buy stuff. If it's consumable stuff like rotors and that sort of stuff, like we understand stuff, even if it's not consumable when you're flying things, right? So it's not like the end of the world of stuff breaks, but we do have this limit. Right? There's only so much we can do there. You don't have to use the, like, and if you already know, like, that you don't want to use the same kit type stuff, like, we don't have to buy you that kit, right? Like, but whatever you're buying, try and get orders in earlier rather than later. Because it always takes longer than you think to incorporate stuff. So we're in the fortunate position of starting in November, which means that you should hopefully be able to get stuff running. It might be Thanksgiving pretty soon, and then it's the end of the semester, but sometime in December, by December, maybe you should be able to get something up and flying, and then be working on improving and designing, figuring out what you want your final product to look at. Yeah.
Again, as a newbie, how does the experience going to realize?
So, does somebody who's done this in the past want to investigate that?
We make it so easy. You'll connect to NASA folks. If you're doing Amazon, you send them the information. They know you.
They order.
Yeah. You should do research reports. Send them the link, the pricing, and all that. And then get it over to them. They're really.
We're not getting like fools.
You have to just talk to them because
There are some limits.
so because there's some places we don't. And I don't know who.
So NASA has restrictions on buying stuff from some foreign. Direct from China stuff is hard. So sometimes what that means is you end up having to pay more for the thing because it's sold by some like reshipper thing who's just buying it from Alibaba.
But marketplace. It's,
Amazon's fun. Amazon's fun. So even if it would be, yeah. Yeah, Amazon's fun.
I have a question on the motors. For our kid, we banged up those motors for a long time.
Yeah.
Do we have new motors or we just?
Yeah, we can order more. So what we're going to do today is we're going to take a look at the inventory, and we're going to have whatever teams have kits today. I think we have, Northwestern, you still have your kits, right? So that's one team, but I didn't bring it back. No, I think we have 4 other kits. So that, I think covers 5 teams, I want to say. And then we'll have to order for the other 2 teams. For anyone that has a kit today, I have a checklist here that you'll go down and we'll mark if it's not working, we can just buy it to replace it. And hopefully that won't come out of here. I'll have to negotiate with them because we have more teams than they anticipated and they like performance. We'll make it work somehow, and I want to make sure it's like relatively fair between people who've done this before, experience, but also they might have some gear on their own. We're trying to get it as even a playing field as we can. But yeah, so if there's something that's not working, or you're like, it's pretty much not working, you just mark that, we can buy you a new set of motors. If you prefer, rather than having the default set, if there's a different set of motors that you want set, you know, let us know. Maybe just count those as the replacement, or if it's like a large price, and then might be able to do the delta. Or, we'll figure that out. But yeah, we want to mark that all down today so that we know if we're placing those orders, we can get those initial set of purchases done. And order early. Don't be afraid to spend money, but if you can get the same performance with less money, that's fine. We're happy with that. So that's ordering stuff. One thing I'll say is that the final price of your quadcopter, of your final simple quadcopter, including whatever modifications, can't go over $1,000. So you can have more than $1,000 worth of stuff that you're playing around with. You can have stuff that your robotics club and your campus buys and whatever. But the final, just to try and keep them even, so it's not like somebody's coming in with like super expensive stuff compared to other people who don't have it. You know, just keep track of what the component price is at reasonable retail prices.
we can check that.
I mean, I'm planning on doing like if you have your bill of materials, if you're buying bill of materials, I think it's
On the day of judgment.
I don't think the judges are looking at that specifically, but I think it's a generally, you know, I used to advise teams, I would all have them have advise them to have the bill of materials with for each component. This is good advice for you. Have the price and the weight. So like, because that you can just sum them up as far as what that is. You might not have weight for like individual screws.
Is there a reasonable estimate of the value? So the price and we incorporate anything that offset
Yeah, so I will provide this thing here. Yeah. Well, it's because, so this is the issue is, so it depends, it really depends on the flight controller here. When we redesigned this, something like that, we went with a flight controller, the Pix Racer, that then got more expensive, and then also got the original version discontinued, and then new. So like, you know, supply chain / individual companies. So right now, if you want to, you can go on and find from AliExpress the same thing for like $130. But if you buy it, like the only place to buy from the people who actually originally designed it is like $350 just for the thing, and then this kit here from Amazon is $416. Like that's a significant jump. You can get different flight controllers, and if you're designing your own thing, it's most of the like there's a difference in flight controllers between this sort of thing, which has like stuff you can easily plug and unplug, versus if you go to like get FPV. This is a great site for if you're, hobbyist stuff like that. We will look at the electronics flight controllers. So here you can find lots of really impressive flight controllers for like $60, $90. This one right here is $290. This one's a really good one. This one has the things that you can plug in. It has like everything wired to it. All of these other ones, a lot of times will have great inertial units inside and that sort of stuff, but they tend to be, so if you look at this, you're direct, like surface mounting or sometimes through mounting and soldering directly onto it for the different components that you connect. This is more for like, it's if you're fine with soldering and desoldering stuff to switch out components or whatever, like these are good and actually they save you weight and obviously price, but yeah.
So a lot of those.
Yeah, that's correct. Yeah. Yeah, depending on what capabilities you need. Yeah.
What's this website?
Get FPV. I mean, just write this one down. I can put it. So I'll talk about communication in just the next slide. Let me. So this is actually something I was going to mention. So rather than going with the PixRacer, which is what when we have some students record some video trying to tell something using the PixRacer. We could instead, I have some alternate flight controllers here that are a lot cheaper that give you more headroom. So like we had more headroom when we originally designed it, now there's zero headroom. So you have to pull out stuff to replace stuff if you want to stay under that. So here, yeah. I mean, if you can, yeah.
But that means now I have to research what it costs today versus what it costs first.
I mean, I can change this limit. So, do you want me to put it at 1,200? We just need a limit. 1,200.
I'm just trying to figure out.
The inflation adjustments. All right. The 1,200 limit. All right. So you have. I'm willing to change that again, but once we get into the spring, I don't want to start changing it too much. Yeah, no, that's good. I didn't take it as a complaint.
It is valid. Change prices.
Yeah. And so here, like the Pixhawk 6X, this one is actually really cool. It has redundant inertial systems. So one, it has an issue with whatever it goes over to another. Yeah, I'll show this as well. And then this is the 6C. It doesn't have the redundant stuff, but it behaves pretty much the same as this one for like $100 less, right? So like there's a lot of options out there for that. I would recommend, especially if this is your first time doing it, sticking with one that lets you plug stuff in and unplug stuff. Because you're gonna mess stuff up, you're gonna want to unplug. It's gonna be better, even though these are more expensive than the other ones. All right, so I think that's it. Last bit, we have a mentor. I don't know if he's here yet. He's not, I don't see him. But Joe Hawker is now at TCSU. He's a former challenge participant. He helped out with last year. He has the contact info. And there's a Discord. This is up and live right now. And so that's what I was saying as far as like sharing this stuff. I'm planning to put resources and things in the Discord. So if, I'll just show you this to you real quick. Here's the Discord. There's a welcome and rules. So when you join, follow those rules, change your display name so that it's a real name so that it's easier to figure out what's going on. I'll put announcements and notes and resources. So I already put, I might have to update this because I think I changed some things, but like this is a PDF of the presentation today. I also have a PowerPoint of it with, PowerPoint's large because it has like videos in it. But this is up there. I'll add these, like that Excel thing with the kit things, I'll put that stuff up there. And then there's a general and an off topic. So general is like whatever you want to talk about, put it there. Related to the quadcopter. Off topic is like maybe there's a request for proposals for in the spring that I want to. Maybe you have a cool thing you want to talk about. So we can make new text channels if like it's like, oh, there should be one of this. And then there are also some voice channels if you want to hop in and talk to people. So and then archives from all right. So that's that. I'll try and be responsive on Discord. Like, don't expect me to talk all hours. I also have my email. I try to be responsive on that. But hopefully this will let you communicate with other people. It's a challenge. It's sort of a competition in that you get points and people can win things, but there's no like cash prize. So it's really about the collaborative effort of trying to help each other learn and grow. And then obviously you want to try and like do the best you can, right? But when you run into issues, you're like, oh, we're running into this. Other people might have had or already solved. Maybe they're still having the same issues. They can help troubleshoot stuff. Be like, hey, here's what helped me, or here's a link to a website that has good video or good explanation.
With a resume and jobs.
Yep. All right. So I know that was a little bit on the long side. What we're doing now is we're going to eat, and then we will. I had a thing for questions, but then we'll do the inventory. So I have these for. We'll get the inventory. So go ahead and grab some food right now, and then we'll make sure we get the stuff packed up to different campuses. And for people who don't have something here physically today, we'll have you take a look at what's in the. Stop my recording.
Right.